is you cannot plug the x in of 0 because this would be undefined. But if we graph this and we look to see as it approaches 0, remember we had points of discontinuity where the graph looked like it was filled in over that circle. We have points of discontinuity. We have where it does reach a certain number. It would approach that number. Now, an easy way to do this in your table is to, once you determine which one you're looking at, say the 0, to go to make your increments be 0.001, look to the left, look to the right. If these are the same, that's the number it's going to approach. If they're different, it's not going to have a limit. It's going to jump. Question? It's going to jump. If it approaches that same number, it's going to have a limit there. If you put this in your calculator, it's going to look like the 0 is already filled in. If you look at your table, it's going to say error because you can't use a 0 for x. So we want to say, as x approaches 0, what number would it meet at from both ends? If it could meet at the same number from both ends, then it has a limit for that. If it doesn't, and it approaches from two different numbers, then it has no limit. Or sometimes your graph does this. One goes this way, one goes this way. This will never, ever, ever come together. That's without bounds. It has like straight up, it will never connect together. Most of these you're going to see, like if it made a line, you would never know that this side had a point of discontinuity until you looked at your table. And we could fill in like we did when we did point of discontinuity, reduce it, find your y value. So if this was a point that I could fill in, I could remove, I would know what point it was. Today we're going to work those out algebraically. Does this make sense? Really? Get the notes, go to the Moodle so that you can figure that part out. Here was a sine curve. So notice you can't put a 0 in there because you would have an undefined fraction. But as x approaches 0, your sine curve approaches 1. Okay? If the number is from both sides. Now, the book and I do it differently. The book goes from 0.1 to 0.01 to 0.001. It gets closer and closer to that number. I usually just do the 3 decimal places from both sides, and you can really see it a little bit closer. Whichever way you choose to do it is fine. Now, this one, this particular one, does this have any restrictions in it at all? Is there any x that I couldn't use in here? There's no restriction, right? So therefore, I should be able to put the 2 right in here. This limit does exist, and it is a number. So whether it turns out to be a real number that is already there, or a number that it approaches, it works the same way. It has a limit. This part of your statement had no restrictions on it. So all we have to do in this case is plug it in. It reaches that number. It is that number. Aaron?
So how do we do this?
All you have to do is plug 2 into this. When you put this in, you're going to say, what's going on at this point right here? Oh, this point right here, when it's 2, it really is 1. That's a valid point. So that's our filled-in point right there. So the limit as x approaches 2 is 1. I'm able to find that value. So whether I can't find it and I'm approaching the same number, or I can find it, I still have a limit at that x value. Okay? That's probably one of the more difficult concepts to catch, that I am having a limit when I can replace it as well. Again, this one has no restriction. Is there any restriction in the denominator at all? No, it has no restriction. So as I approach -1, and I put -1 in here, so negative 1 pi over 2 is negative 90, right? So what is the sign of negative 90? The sign of 90 is 1. The sign of negative 90 is negative 1. I have a value there. That value exists. So my limit does exist. My limit is its y value. What we determined on Friday also was, you have to remember, when you look for a value of a function, you're looking for its y value. The value of this function at x equals f at x. We used to say f at x. And we want the value of the function. We want the y. Now, whether we can find the y exactly, or we can find as it approaches that same y from both ends, that's called its limit. We actually did this. We did point to discontinuities. We're rewording, we're calling this now by the calculus terms. These are what limits are. You'll see more of it today when we solve it algebraically. This guy, if you look at your denominator, here's your restriction. X plus 2, when x is negative 2, you have a domain restriction. Therefore, you cannot use negative 2. So I want to know, is there a value as x approaches negative 2? Do these approach from the same side? And look, they don't. One approaches negative 1, one approaches 1. Could they ever meet? No. This limit does not exist. And that's how we write it. It does not approach the same number from both ends. Well, in other words, from both sides of it. And you could kind of see it does a little jump. If it jumps, there's no limit. It does not approach the same y value. One is a negative 1, one is a positive 1. Good? Do you see the difference between this one and the other ones? Okay. And these last couple, notice that x cannot be 4 in your denominator. That would make it a 0. So we graph it, and we fine-tune it. Again, start at 4, start your table at 4, and increment your table by 0.001. This way, as you approach this, you should see these two guys approach the same number. If they approach the same number, we have a limit. And the limit is that number. And I technically only need 3 decimals, so you can give me 3 decimals, 4 decimals if you prefer. It's very hard to see. It looks like it's a continuous line when you graph it. If you go to your table, when x is 4, it says error. This is our point of discontinuity. If I could remove that point by finding its y value, I would have one continuous line. So the limit as x approaches 4 is this y value. We just kind of looked at these graphically. We graphed them. We saw, did they approach the same number? Did they not approach the same number? No limit if they don't approach the same number. The limit doesn't exist. If they do approach the same number, we have a limit. God bless you. This one, again, your denominator is where your restriction is, so we can't use 3. Excuse me, if I plugged in 3, it would say undefined. So, do I reach the same limit? Do I approach the same number? This is called without bounds. My boundaries, my end behaviors, are in different directions. This one caused this end behavior. This one caused this end behavior. Will they ever meet at the same point? Without bounds. So this limit does not exist. You look for where x is 3. X is 3 is your asymptote this time. See it? This is your asymptote when x is equal to 3. That's an asymptote. We're actually revisiting the things we learned before. We're going to also revisit, like when we found your horizontal and your vertical asymptotes, we're going to revisit those too in calculus terms. So you're kind of redoing what we did, and remember, I don't know if you remember when we did this, I said we would revisit this again and call this guy what we call it in calculus. And you can still graph it so that you can look at. Remember, you're looking at your domain. You want to look at your domains. Shh, guys, stop. You want to see, can I put this x value in with no restrictions? Do I have restrictions? Do I need to factor and cancel like we did when we found your point of discontinuity? Should I just use my calculator to find this? Some of them you're going to just use your calculator for. So we're going to start with a direct substitution. Now, look at this function. It's a parabola. So you say to yourself, is there any value of x that I cannot use? Is there any restrictions, like a denominator? None. No absolute values, no radical signs. There are no domain restrictions. So I should be able to take this value and plug it in. I take this value and I plug it into x. So I say, okay, when x is 4, plug this in. Put that in your calculator and find the y that it returns. So we put it in and we find 19. So this limit is at 19. As x approaches 4, and we know 4 has a value, its value is 19. If there are no domain restrictions, you can plug them right in. So one good thing to do is to put it in perspective. Figure out what does this function look like, a parabola. Put it in your y equals. That's always a good thing to do. And you kind of get a feel for what's going on. So our first one is direct substitution. Good? Stop me if you have any questions. And we looked at your graphs, and we saw that on your graphs on Friday. Now, the second one, if I put this in, I get a line, and in my calculator, I can't tell that there's any problems. But when I look at my table, I notice that -3, says error. Because my domain restriction says, oh, you can't use -3. That's going to give you an error. But my graph looks like it's complete. This is my point of discontinuity. So what I want to do is to look at it from both sides like we did in your graph. And we could see what would this be as we approach -3. We did this with your graph. Today, algebraically, we're going to say factor and reduce it, then plug the x in. We did this when we found your point of discontinuity.
What does that say at the factor?
Factor and reduce. Sorry. This is your point of discontinuity. And remember what we did? We factored it. We reduced the common factor, which turned out to be the x value for your point of discontinuity. And then we plugged it into the remaining function. So we factor the numerator. We have an x plus 3 and an x minus 2 over an x plus 3. So we take out your common factor. Notice this is what your x is. X plus 3 equals 0. That's where your discontinuity is, at this x value that we factored out. Now, what remains in our function is x minus 2. So the same thing we did with your point of discontinuity, we took your -3 and we plugged it in to your x minus 2. So algebraically, this limit is at -5. Graphically, when we looked at this on Friday, we looked at how this approaches. Doesn't that approach the point -5 from both sides, right? Graphically, this is what we did Friday. We looked at it graphically. Today we're looking at it algebraically. But it has to make sense. This is your typical point of discontinuity. I take out where my domain restriction is, take out that common factor, and then plug in to the remaining function, the reduced function, when it's reduced. Okay? So my limit as x approaches -3 is equal to -5. It's your y value. Remember doing the point of discontinuity like this? That's a while ago. You're going to have to remember those anyway, because that's going to be on your final as well. Now, here's another cutie. And again, you notice if we plugged in a 1, if I plugged in a 1 down here, 1 cubed would be 1, 1 squared would be 1, 1. What would my denominator be equal to? 0. So I can't do this. I have a restriction. So in order to do this, I'm going to do the same thing that we just did. We're going to factor and reduce. This is good factoring skills for you guys. So we're going to take this denominator, we're going to factor it. Because there's 4 terms here, we're going to group. We're going to group these, we're going to group these. What can I factor out of the first group? X squared. So what's left? X minus 1. X squared over x squared is 1. Now it looks exactly like this guy, doesn't it? So just factor out a 1. Take your common factor, and then this is your remaining factor. Okay? That's your remaining factor. Now, we're going to use this in the denominator in place of what we had. So now we can eliminate your common factor, which becomes your point of discontinuity. So what's left in the numerator? 1. So here's what's left of my function after we factor it. So how do I find its y value? Substitute it in now. Now I can substitute it in. Now I can say when x minus 1, so x is 1, there's my limit. When x is 1, plug it into this. 1 squared plus 1. Now I've eliminated my problem that I couldn't do before. So 1 half. 1 plus 1, 2. So my limit of this guy is at 1 half, or 0.5. Now, graphically, doesn't this work? Doesn't it approach 0.5 from both sides? We did the graphic part Friday. All we're doing this time is the algebraic part. Your point of discontinuity happens when you factor, you have a common factor that you can take out. You find that x value, which is probably where your limit is reaching, and then you plug in for y and find its y value. Good? There are no questions? Okay. Alright. This one, not such a pretty one. But we're going to rationalize this guy. Now, normally, you rationalize your denominators. However, this time around, we rationalize our numerators. Because here's my problem. I can't plug a 0 in for x, right? I can't divide by 0. So I need to be able to eliminate my denominator. There's nothing I can multiply the x by right now. So we're going to rationalize your numerator. Same thing you did when you rationalized your denominator. Same terms, opposite signs. So you're going to multiply the numerator and the denominator by its conjugate. The conjugate of the numerator. Okay? So we're multiplying this thing by that. Now, just stay with me. So first terms, this guy times this guy. The radical comes out, right? We get x plus 1. Radical x plus 1 times 1 is radical x plus 1. Negative 1 times radical x plus 1, negative radical x plus 1. Negative 1 times positive 1, negative 1. Our middle terms cancel out, right? Because aren't those perfect squares your conjugates? So in perfect squares, can you just multiply your first terms and your last terms? I wanted you to see that the middle terms cancel out, because they look a little strange for being perfect squares. But look, first term, last term. So automatically, first term, last term. So you don't have to do the middle terms, because in your perfect squares, they will cancel out. Now, take this guy and don't multiply this yet. Slide this over. Your goal is to reduce this. So if you distribute it, you're going to have to factor it back out. Let's collect your terms on the top. A negative 1 and a positive 1 cancel out. So you're left with x over this guy. Yeah, it's not so pretty. However, what happens to the x's now?
Wait, why did you cross it out with the plus 1 from the x if it's like
Because
together?
I'm collecting like terms. This is what's left in my numerator. X plus 1 minus 1. First terms, last terms. We canceled out your middle terms.
So the x plus 1 is the same as the negative 1 on the end?
Well, you're going to combine your like terms now. So what happens to a plus 1 and a minus 1? They're not being multiplied, they're being added now. So they cancel out, don't they? If I multiply my first terms, watch. It comes out of the denominator, it comes out of the radical. Multiply your last terms. Combine. What's left? X. Okay? Now,
So they're all separate?
yeah, they're just separate terms. They're not being multiplied. We multiplied them already and took them out. So now we just have to combine like terms. You know like how you combine like terms in the middle? You just combine your like terms.
Mhm. Got confused with the x plus 1.
But the negative 1 and the positive 1 can cancel out. They're not multiplying, they're terms. There's 3 terms, an x, a 1, and a negative 1. So a 1 and a negative 1 can cancel out. Okay? Now, out comes this x. Wasn't it our goal to get rid of that x? And a 1 is on top. Now, as bad as this guy looks, we can still use this. Because now I'm going to plug in x is 0, because I wanted to know the limit as x approached 0. So I plug this in. So I get 0 plus 1. Now, order of operations, what is the square root of 1? 1. And what is 1 plus 1? 2. So this is equal to 1/2. And graphically, wasn't that going to come out to be 1/2? Guys, this is just algebra. Find your conjugate, which is your perfect square, and multiply it. That part's just algebra. Use your conjugate of your numerator. Alright? Now this next one should be even funner for you guys. Much more funner. Alright, I have a complex fraction. I want to know the limit as x approaches 0. If I plug a 0 in here, look what happens. Can I divide by 0? So we need to get rid of that 0. So we're going to take this fraction first. And we're going to find a common denominator. Put this over 1. What's your common denominator? I need a 5, and I need a 5 minus x. So on the top of every term, 5 times 5 minus x. Use your common denominator. So in the first term, what can I cancel out? 5 minus x. What's left? 5. Minus, what can I cancel out? 5. And I'm left with parentheses, 5 minus x. Your goal is to get rid of your complex fraction. Now in the denominator, you're just multiplying. So let's multiply 5 times x times 5 minus x. Leave the denominator, don't distribute it. Work the numerator. You got to get this guy out of the parentheses. So minus 5 plus x. And what is 5 minus 5? 0. That cancels out. So we're left with x over 5x, 5 minus x. Our goal was to get rid of that x. Can we cancel out the x now? Top and bottom, isn't it a factor? So what's left on the top? 1. Now I can plug in the x of 0. So I get 1 over 5 times 5 minus 0 is 5. I get 1/25. Okay, which is the same as 0.04. Graphically, I can look at the table and see that was 0.04. 0.04 is the same as 1/25. Yes. Yes. How did it become positive? Because it's negative. Guys, hang on. Negative times a negative. Okay, hang on. I have 2 more, I think, here. One more? Okay, one more. All right. Piecewise. A piecewise function says I'm going to use this function when this is my graph. So I want it to end at 1. Remember doing this? I want it to be closed at 1. And this guy, I want to start at 1, open. But all I care about is this piece right here. Is it going to meet at that point? So I plug the 1 into this. I get 4 minus 1 is 3. I plug the 1 into this. I get 3 minus 1 is 2. Did these meet at the same point? No. So the limit does not exist. Limit does not exist. I know we went through a lot.